Welcome back. Today we're going to be looking at zeros of polynomial functions. It's going to use a lot of the skills from long division and synthetic division to solve for specific results where we have factors and zeros. Let's go ahead and get started. The first thing I want to talk about is this word zero, which we see pop up a lot in math, and I like to define this rocks definition. Every time I see the word zero, I like to talk about rocks, which is roots, zero, x-intercept, and solutions. All four of those words kind of mean the exact same thing, so if you see them interchangeable in a problem and it says find a solution, find a root, find an x-intercept, find a solution, you're looking for a zero or a place where that function crosses the x-axis. And the way that you find these is you find factors and set them equal to zero. So if you find like a factor of x minus 2, you set it equal to 0, you've got yourself a root, using that zero product property for multiplication. All right, so the first cool little thing about this is a remainder theorem that we have that just allows us to solve problems in a different way, though you could just plug and chug. This remainder theorem says if you have a factor, or a potential factor, we don't know if it is until we synthetic divide, and you have a plug and chug problem where you just plug a normal value in, finding the remainder is exactly the same as plugging and chugging. Is that true? I don't know. Let's find out. Backwards L. We've got ourselves our potential factor or our potential zero. We don't know for sure if negative 3 is a 0 until we synthetic divide it. And then we need to pick our coefficients, being careful to look out for those missing ones. So we've got 5, 4, 3, 2, and it looks like they skipped the 1. So don't forget to add a plus 0x to the 1. And then the constant, we're good to go. So we'll use those coefficients of 2, negative 3, negative 9, 8, 0, and 2. Drop down the 2, and that is setting up synthetic division. If you don't remember entirely about setting up synthetic division or how to do it, the process of multiplication around and addition straight down, then you can go back and watch the synthetic division video or read through the textbook of section 5.4 to really try to master synthetic before moving on. All right, so let's get started. I'm going to go ahead and start our multiplications with 2 times negative 3 is negative 6. We've got ourselves an add them up, negative 9, positive 27, positive 18, 18 times 3. If you need to pull out a calculator or you need to go off to the side and solve it, that's okay. 18 times 3 is negative 54. Negative 54 plus 8 is negative 46. Negative 46 times negative 3, it's 138. Add those, that's an easy add, 138. Kind of a longer one, 138 times negative 3 is negative 414. And then if you add those two things together, you get negative 412 as your remainder. And what this remainder theorem says is, hey, instead of plugging and chugging, we could have just added, multiplied, added, multiplied, added, multiplied to get our synthetic division. Take that remainder and say f of negative 3 equals negative 412. If you want to check your work, you could plug and chug negative 3 into our original function and see if we get the exact same thing. I'd highly encourage you to do that. Often in class, I'll have half the class synthetically divide it and half the class plug and chug and see if we get the same thing. So it's a good idea to check your work that way. All right, now here is the crux of the whole thing. Nope, the remainder theorem's on there twice. It's still good to know. I'll go ahead and, you don't need to memorize it twice. It's the exact same theorem. But what we're going to do is we're going to hop down and try to talk about the factor theorem. And so the factor theorem says that if you take the same, it's almost like the remainder theorem, but if your remainder is equal to 0, then k is a 0. Or if your remainder is equal to k, then x minus k is a factor. So look for that in the updated notes as I fix that, and let's go ahead and I'll show you what that looks like. So we're going to do the exact same thing. We're going to say, look at that 2, our x minus k, so k equals 2. So 2 goes inside of our synthetic. What goes on the outside, we've got to, let's check those exponents, 3, 2, 1, 0, we're good to go. We're checking the exponents to make sure we're not skipping any. 1, coefficient, 4, -4, and -16. Drop down the 1. 1 times 2 is 2. 6. 6 times 2 is 12. Positive 8. 8 times 2 is 16. Here's where the cool thing happens. 16 minus 16 is 0. Square it. And I'm going to write right next to it. That means that you got an x-intercept. And so if you go over here, you could say 2 is an x-intercept, or a 0. And so what we've done is we found one of our zeros, one of our x-intercepts, and by default we can go ahead and off to the side and write, we know a factor. If 2 is 0, that means that x minus 2 is a factor. Two correlated facts that are really important to know, and then we'll backfill with x and x squared. And so what we've got now is we've got a polynomial that looks like we can solve it. And if you remember factoring polynomials, you drop down that 8 and you say, are there any factors of 8 that add up to 6? Positive 4 and positive 2. Add up to 6, multiply to get you 8. And so if we were to factor that quadratic, x plus 4, x plus 2, and don't forget the factor we've already taken out with that positive 2, x minus 2. And so if we were to synthetically divide that whole thing, or if we were to factor the whole thing, or if we were to FOIL this new result, we'd end up with the exact same thing that we started with, which is that long f of x up there. It says to find the zeros, though. It doesn't say to factor. So though that is the fully factored form, fully factored, we're going to go ahead and use that fully factored form to look at the 3 independent zeros we have there. If you remember back from a previous section, they each have a multiplicity of 1 because they each have an exponent of 1. So that means they each cross at the x-intercept. It's just a lot of recall. So our zeros. Let's find the zeros like the problem asked us to. We've got -4, comma 0 from the first term, -2, comma 0 from the second term, and 2, comma 0 from the third term. All right. All right, let's keep going. We're going to look at what if they don't give it to you? What if they don't give you one of these potential zeros for you to check with? What do you do? And so that's where we use this rational zero theorem, which is a way to find possible rational zeros. Possible zeros that you can synthetic divide and check with. And so they use this P over Q is the most important thing here. If you look at that P over Q, it's over here, P over Q. This P over Q is really, really important, where P is the last term or the trailing constant, and Q is your leading term. So P over Q is the same thing as the trailing coefficient or the trailing constant. I'm going to write that out. The trailing or the last constant, and Q is the leading coefficient on your leading term. Sometimes in class I'll say if P over Q is too hard because you can't remember where something is, you can remember TC over LC as well. So P over Q is TC over LC, or the last over the first. And so we're like, okay, well, what do we do? How do we make this happen? Well, we look at our equation or look at our long polynomial and we say, boom, boom, there's our trailing coefficient or our P. We look at the first thing and say, yep, we're missing a 1, but it's still there. There is our leading coefficient, or there is our Q. And then we take those two things and we say TC, this is going to be 1 over 1. TC over LC is equal to P over Q, which is 1 over 1. It's going to be a kind of easy one to start with. But 1 over 1 isn't our possible solution. 1 over 1 is just an informative ratio that's going to, so I don't draw an equal sign, I'm drawing an arrow. I'm going to ask myself, what are the factors on the top and on the bottom? I'm not setting it equal. I'm just asking myself to expand on this and say, what are the factors of 1? What two things multiply to get me 1? Well, positive 1, comma negative 1 on the top, and positive 1, comma negative 1 on the bottom. And so what that means is we have a set of possible rational zeros of -1 and 1. And what I'm doing is I'm checking all the possible combinations of the top and the bottom. So I'm going to check 1 over 1 is 1. 1 over -1 is -1. -1 over 1 is -1. -1 over -1 is +1. So we're checking every possible combination of the top and the bottom to see if we get a new possible rational zero. And these are called possible rational zeros. And then what we do is we find, we synthetic divide them. We use those two new possible rational zeros to see if either of them are zeros. And so I take the 1, put it inside the circle, 3, 2, 1, 0, we're good to go. We don't have to add any zero terms, and we go 1, -5, 2, 1. That's me just pulling in those coefficients for synthetic division. 1 times 1 is 1, -4, -4, -2, -2, -1. Circle it. That's a remainder. A remainder of 1 means that 1 is not a 0. So we got to try the other one. So what I'm going to say is these were possible rational zeros. I'm going to cross it out and say it's not a rational 0. It was possible, but it's not. Let's try -1. -1, backwards L, 1, -5, 2, 1, drop it down, 1. 1 times -1 is -1, -6, +6, 8, -8, -7, boom. We got ourselves a remainder of -7, which means -1 is not a 0. Well, there were no other possible rational zeros, and so this says use the rational zero theorem to find rational zeros. There are none. Their f of x has no rational zeros. Though it had two possible rational zeros, when we synthetically divided them, we found that it had no real rational zeros. All right, let's keep rolling through it. And here we've got the fundamental theorem of algebra, which kind of just says what we've already been working on, is if you synthetically divide and factor them out, you can get a set of whole factors where every c value was one of those possible rational zeros. And you have exactly n linear factors where n has to be your degree or greater than your degree. All right, let's find it out. So here we're going to do the same thing. We're going to take this TC, we're going to take this LC, and we are going to find our possible rational zeros to start. So TC over LC, or P over Q. Remember, this is P. That's Q, is 4 over 2. We ask ourselves, what are the factors of 4? Positive -1, positive -2, positive -4. What are the factors of 2? Positive -1, positive -2. So there's all our potential factors, and we're going to expand that by checking each combination and writing a set of what we call PRZ, or possible rational zeros. 1 over 1 is 1, plus or minus 1. 1 over 2 is 1/2, plus or minus 1/2. 1 over, oh, that's it. Now move to the 2. 2 over 1 is 2, plus or minus 2. 2 over 2 is 1. We've already accounted for 1. We don't have to do it. So I took care of the 1, took care of the 2. 4 over 1 is 4, so plus or minus 4. 4 over 2 is 2. Well, we've already written it there. So that is our set of possible rational zeros. 1, 1/2, 2, and 4. And now we just use those to synthetically divide. I'm going to start with 1 because I like to start with 1. I always start with 1 and -1 because they're the easiest to synthetic divide, and see if we get any zeros. So here we go. Let's take 1 and synthetically divide it out. So 1 divided by 2, 5, 11, and 4. Did we skip any? 3, 2, 1, 0. We're good to go. Drop down the 2. 2 times 1 is 2, 7, 7, -4, -4. Hey-oh. First try we found it, which is awesome. 1 always happened, but that was nice. So what that means is that we found that x minus 1 is a factor. Because it ended in 0, we found ourselves a 0, and x minus 1 was a factor. Backfill in our constant, x squared, and we've got ourselves another thing to try. So here's an option that you have. You can either keep synthetic dividing, trying out your things, or you can move straight to quadratic factoring like we know how to do from previous sections. I prefer quadratic factoring because I know I can always use that quadratic formula to finish the problem. But if you prefer to keep going synthetic and trying all of the options, you're more than welcome to do that. I'm going to hop to factoring though, where I'm going to do maybe a slide and divide method that I've shown you a couple times. Slide the 2 over, you end up with x squared plus 7x minus 8. So that's the slide step. Then you factor normally, so you've got x plus 8, x minus 1. Does that work out? It does. Then you have to do the divide step, where the number that you slid, so we slid by a multiply 2, we divide by 2. Then you reduce, so we're going to reduce it to x plus 4 and x minus 1/2. And then you do your last slide to make a slide sandwich, where you slide, the first step you did was slide the 2 over, the last step you do is slide any fractions to the front, and we've got ourselves x plus 4, 2x minus 1. That's the same exact steps as the AC method, just shown in a different way, where you slide and divide. The AC method, remember, is the one where you draw an x and you multiply a times c, and you find factors, and you factor by grouping after finding them. They're both totally valid ways to factor. You can pick which one you like the best. You can watch some YouTube videos and see which one you prefer. All right, so we've got ourselves our factors now. It said find the zeros. First, before I find the zeros, I want to find fully factored form, just so I remember what we did here. So we have x plus 4, 2x minus 1, and where was our first factor? X minus 1? X minus 1 out there. And so if we set each of those factors equal to 0, we'll get our zeros. Our zeros were x negative 4 comma 0 from the first one, negative 1/2 comma 0 from the second one, positive 1/2, and 1 comma 0. And the question to ask yourself is, were those all zeros that were potential rational zeros? Look right there. We got our 1, we got our 1/2, and we got our 4. So it seems to check out that those were all possible rational zeros, which is a great result. So we have our zeros, and we have our fully factored form up above if you wanted to do that as an extra step. All right. We need to talk about this complex conjugate theorem, then we'll wrap it up for this section. The complex conjugate theorem says, well, what if you got to that last step? I know this is getting messy, but what if you got to that last step right there where you got a quadratic equation and it didn't factor nice and neat? You were going to get a complex answer. You were going to have to use the quadratic formula. Well, what this complex conjugate theorem says is, if a complex number is any factor, then its conjugate, which we talked about in dividing complex numbers, also is a 0. You can't have one without the other, because you can't have the quadratic formula without a plus or a minus right in the middle. And if you have to resort to the quadratic formula to get a complex number, you got a plus or a minus, which means you're going to have the complex conjugate. And so what does that mean? Well, that just means if they give you some zeros, so it says find a third degree polynomial, that means n equals 3. It means the highest degree, or the highest exponent is 3. It has a 0 of 5, which means if we have a 0 of 5, we have a factor of x minus 5. We have a 0 of negative 2i, which means we have a factor of x minus negative 2i, which is technically, if we want to make that a little prettier, x plus 2i. And this new complex conjugate theorem says that if you have a complex solution, or a complex 0, or a complex root, or a complex, well, it's not an x-intercept, then you have its conjugate hanging out there. So you have negative 2i as well. And those are our 3 roots, so we can go ahead and solve now. So we've got f of x is equal to a times x minus 5, x plus 2i, and x minus 2i. And now our question is, well, how do we find that a? How do we find that leading term? They've given us a point to plug and chug. And if we plug and chug that point, we can hunt down that leading term just fine. So let's do it. Plug in 1 to x. So f of 1 equals 10 equals a times 1 minus 5 times 1 plus 2i times 1 minus 2i. Looks like we're going to have to do some multiplication here. I'm going to start with this complex section because it'll probably get rid of the i's. That's what conjugates do. So 1 times 1 is 1 plus 2i. So first was 1. Inside plus 2i. Outside minus 2i. Last minus 4i squared. Notice those two i's go away. The I squared turns into a -1. So we're left with 1 plus 4, which is just going to be 5. 1 minus 5 is -4. Got ourselves an A, and we leave the 10 alone. So now we've got 10 equals A times -20, which means that A equals 10 over -20, or A equals -1/2. And now we've got our A and we've got our fully factored form, so we can just plug that A in and be done with finding the equation because of that complex conjugate theorem. So f of x is equal to -1/2 out front, x minus 5, x plus 2i, x minus 2i. All right. I'm going to leave try at 7 for the sake of time for you to try on your own. It is just going to be synthetically dividing a couple of factors where they tell us. I'll set it up and then I'll let you work on it. So it says we've got a volume of 84. It says we got a length. I'm going to highlight this. Length of the container must be 1 meter longer than the width. So the length equals 2w plus 1. The height must be 1 meter greater than twice the width. So the length of the container must be 1 meter longer than the width. The height must be 1 meter greater than twice the width. And what we're going to do there is we're going to just find our formula for volume. We know, if you remember back in the day, was L times W times H, or multiplying all three edges. And so we've got a volume 84 equals W plus 1, 2W plus 1, and W. And now we've got a fully factored form where we could go and solve this equation. If you move the 84 over and get a 0, you do a little distribution. You could solve for what to synthetically divide. You could find the P over Q. You could synthetically divide some of the answers, and you could end up finding the 3 sides that would equal 84. All right. That's a lot of information for finding zeros and applying those two theorems, the rational zero theorem, the fundamental theorem of algebra, the complex conjugate theorem. It's really important that you go back over this, you practice some of these practice problems, work on exercises in the text. As you work through these practice problems and you have any questions, be sure to reach out to your instructor, who will be happy to help. And also prepare for the test that's coming up as we get through this and have 2 more sections. Our Chapter 5 test will be coming up, and studying for that will help prepare you for success. So thank you for watching this far, and I will see you next time.